Okay, so we're going to continue in our discussion of organic reactions and intermediates. So far we had looked at sort of the types of organic reactions. We saw substitution, and we looked in fact at two types. We looked at SN reactions, where for example we had say chlorocyclohexane reacting with say hydroxide to give rise to cyclohexanol and Cl minus. So this is an SN reaction. It's a nucleophilic substitution reaction because the incoming reagent enters as an electron-rich species. We saw that there were SE reactions where, for example, I think the one I gave you was if we had, for example, benzene reacting with, say, NO2 plus, that would give rise to nitrobenzene. Reaction. In particular, it's called an SEAR, but it's an SE reaction. You can also have radical substitution, where, for example, I take, say, this compound and I treat it with chlorine in the presence of light, and I'll end up with this compound. I'll get Cl plus HCl. So these are substitution reactions. These are nucleophilic substitution, electrophilic substitution, and radical substitution. Okay, so nucleophilic substitution. This is electrophilic substitution. This is radical. The reactions go via substitution, because radical reactions go via nucleophiles here, electrophiles here, and free radicals here. We also started looking briefly at addition reactions. So in addition reactions, there was destruction, well, there was incorporation of a simple molecule, or some people say the elements of a simple molecule, with simultaneous destruction, or loss of a pi bond. And we looked, for example, at if I take this compound, we can convert that into this one, or we can convert it into this one, or into this one, or into, say, this one, Br or something. And this reaction involves using chlorine. This one is a hydrogenation, this one is water, this one is HBr. And the point I made in class is that it's very easy to see when we've brought on a heteroatom. That's fairly straightforward. But it's a little bit less obvious when one of the atoms, one or both of the atoms coming on is hydrogen. So for example, there are two H's here and one here. Now there are three H's here and one and two here. So I put on one H here and one H here. In this particular case, I've put on the OH in this carbon, and I've put an H in this carbon, because at this point there's one H here, now there are two H's. So you want to be very careful when you do reactions, addition reactions that involve anything with H's, because in the bond line those H's will not be written. And I did mention that addition reactions all end in ation. That's a suffix, and the prefix involves what was added. So this would be called a chlorination. Yikes. Chlorination. fluorination. This is a hydrogenation. This is a hydration. And this would be a hydrobromination. I mentioned as well in class that addition reactions need not only involve themselves with carbon-carbon double bonds. I can do additions that involve carbon-carbon triple bonds. So for example, I can add, for example, hydrogen gas to this one and end up with this, or I can add HBr and end up with this compound. Right, so this is a hydrogenation. This is a hydrobromination. And this is a hydro. And in both of these reactions, you notice we destroyed both of the pi bonds. So I went from C3H4, here I'm C3H8. So I literally added 2 moles of H2 across the double bonds. So 1 mole of H2 took care of one pi bond, another mole of H2 took care of another pi bond. I added 2 HBRs here, so at this point there's 1 H in this carbon, now there's 3 H's. So I added 2 H's to this carbon, 2 BRs to this carbon. I could do partial. This is really 2 H2s and 2 HBRs. I could just, add 1 mole of H2 and make that compound. That we call it partial hydrogenation, because I did leave 1 pi bond unperturbed. I could do this also with carbon-oxygen double bonds or carbon-nitrogen triple bonds, and I can get a hydrogenation, which gives rise to this compound, or I can get a hydrocyanation, which gives rise to this compound. So this is a hydrogenation because I added essentially H across the double bond. Right? So 1 H went here, 1 H went here. And then in this case I'm adding HCN. This is a hydrocyanation. I added, an H to this carbon, this O, and an OH to that one. So those are addition reactions. The other class of reaction is an elimination reaction. And elimination reactions are literally the opposite of addition reactions. So these are ones in which there is loss of the elements of a simple compound with simultaneous formation of a pi bond. So it is literally the opposite of an addition reaction. So, for example, I can take, let's say, this compound. We saw this a second ago, and I can convert that into an alkyne. Right? That is literally the opposite reaction to what we saw a second ago. Right? That's the opposite of this reaction, where we took the alkyne and made the gem dibromo compound. I can actually go backwards now and convert this into that. So literally, I'm losing 2 HBRs. Or I can go from this compound, right, and I can make this one. Or I can go from this compound and make this one. Or I can go from, let's see, from this compound and make this one, and so on and so on and so on. So hydrogen or elimination reactions involve the loss of a simple molecule. Now, in this case, I've lost 2 HBRs. In this case, I've lost H2. In this case, I've lost Cl2. In this case, I've lost HCl. And I will caution you again that you want to be careful for additions and eliminations that involve H loss or H gain, because it's hard to see it on the bond line formula. But you have to recognize, for example, in this case, that there were 2 H's here and 2 H's here. In the product, I only have 1 H here, so I lost an H from this. The 2 H's here are still there. What I did lose is the Cl. So I lost 8 Cl here. So this elimination reactions are referred to as D something Ation. So additions are something Ation, eliminations are the opposite, so the D something Ation. So this one I'd call a dehydrobromination. This one I'd call a dehydrogenation. And for those of you who are biochemistry majors or who are pre-meds, there are enzymes in the body that do exactly this. They're alcohol dehydrogenases. And what they do is they convert alcohols into aldehydes and ketones, right? That's the dehydrogenation. This would be a dechlorination, because I'd have lost the elements of chlorine. This would be a dehydrochlorination. Now, there are a couple little subtleties with elimination reactions. So, for example, if I take this compound and I treat it with sodium iodide in acetone, and for now this is not a detail you need to be aware of, what I'll end up with is the corresponding alkene. And I would say that is an elimination reaction, because I've lost the elements of bromine. I've lost, what looks like Br2. These are the elements of Br2, and there's been a simultaneous formation of a pi bond. Now I can recognize the eliminations because at the beginning there will be either no pi bonds. Well, at the beginning there'll be no pi bonds, and at the end I'll be a pi bond richer. Now I could also start off with 1 pi bond and end up with 2. Right? So basically what happens is I am making a pi bond in an elimination reaction. Whereas in an addition reaction, I'm destroying a pi bond. But when I look at the products of the reaction, I actually don't make Br2. What I actually make in this reaction is, at least initially, I make IBr and Br minus, and then eventually the IBr reacts with another iodide, and I make I2 and Br minus. So when I look at the products of the reaction, they are actually the alkene, 2 bromides, and I2. Those are my products. Nowhere in my product is there bromine, which is why in the definition of elimination we don't say that we lose a simple compound. We say we've lost the elements of a simple compound. So if you ask the starting material, what happened to you? It will say, well, I lost 2 Brs, or I lost bromine. Although bromine is not an actual product in the reaction. So elimination reaction does not involve the loss of a simple compound. It involves the loss of the elements of a simple compound, and that's an important subtlety. And it should be very easy to recognize an elimination reaction because we are generating more pi bonds than we started off with. For example, if I take, let's say, if I take this compound and I heat this with phosphorus pentoxide, the product of the reaction is a nitrile. So how would I classify this reaction? Well, I had 1 pi bond at the beginning, I have 2 at the end, and I grant you this one was between C and O, and this is now, they're all between C and N, but that's irrelevant. I have lost the elements of H2O. There has been simultaneous formation of an extra pi bond. So this really is a dehydration reaction. And this is another example where nowhere in the product is water found. So an elimination reaction involves the loss of the elements of a simple compound, H2, H2O, HBr, Br2, and so on, with the simultaneous formation of a pi bond. So I can start from no pi bonds and end up with 1, or 1 pi bond and end up with 2. Okay? The last class of reaction is we've done addition, substitution, elimination, and there's rearrangement. So the last class is rearrangement. And rearrangements are of two types. There is rearrangement of hydrogens in the molecule. Hydrogens across the molecule can sort of move, or I can rearrange the carbon skeleton, which means I do skeletal rearrangements. So for example, let's suppose I take this compound. If I take, let's say, this compound, and I dissolve it, I simply dissolve it in a very polar ionizing solvent like DMSO. DMSO, by the way, is an acronym for dimethyl sulfoxide. It has a structure S double bond O, that's a sulfoxide group, and 2 methyls. It's an extremely polar organic solvent. The product of this reaction turns out to be this compound. Right? So if I carry out this reaction and I take, what I simply am going to do is dissolve this compound in DMSO. Clearly what I've done is I've rearranged the molecule. Essentially what happened is this methyl, or that one, moves over to this carbon, and that chlorine moves over here. So that is a rearrangement that involves a skeletal rearrangement in the molecule. If, for example, I were to take this compound, let's see, if I were to take this compound, I might find that this compound might rearrange into this one. And essentially what happened is I moved a proton from here to here. Basically I moved one of these H's onto this oxygen. So that is a rearrangement, but that involves a shift of protons. I haven't changed my carbon skeleton at all. So this I would call a skeletal rearrangement. In the bad old days they were called Wagner-Mervine shifts, and this is basically a hydrogen or proton rearrangement. So both of these then are called rearrangements, and if you notice, these rearrangements are isomerizations, right? Because I've gone from one isomer to another, one isomer to another. Now often rearrangement are not reactions that happen on their own, although for example in these cases they are. Rearrangements often, but not always, accompany other reactions. So for example, if I started off with, say, this compound, and I treat this with concentrated sulfuric acid, and I heated it, the product of the reaction is this. Now, if I look at this, I would say immediately this is an elimination reaction. And how do I know that? Well, for heaven's sake, I have no pi bonds in the starting material. I have a pi bond in the product. So I've formed a pi bond. That is one of the requirements of an elimination reaction. But if I look, I have an OH here. So I must have lost an OH. I cannot lose OH by itself. I have to lose the elements of a simple molecule. OH is not a simple molecule. But if I look at the formula, to be very careful, it's C1, 2, 3, 4, 5, 6, H, 3, 6, 9, 10, 12, 14, O. The formula of this compound is C1, 2, 3, 4, 5, 6, H, 3, 6, 9, 12, and I have no O's. So literally the difference between C6H14O and C6H12, the difference is literally H2O. So this reaction really then is a dehydration. which means I lost an OH, which was fairly obvious. What is less obvious is I lost an H from one of the carbons. It's hard to tell which one I lost it from because the carbon skeleton is rearranged. So I can't just say I lost it from this one, because that would mean, well, if that was all that happened, it would mean that this carbon would have gone from having 2 H's to having 1. But none of the carbons in the product has 1 H. Essentially what also happened in this reaction is one of these methyl groups moved over to this carbon, and I also lost an OH and an H. So this is a dehydration with rearrangement. Or if you wanted to be, you can also say it's a rearrangement with dehydration, but typically people identify this reaction first as the dehydration, but also it's accompanied by skeletal rearrangements. In a similar fashion, if I had, let's say, this compound, and I treated it with, say, HCl, the product of the reaction would be this compound. And if I were to say what kind of reaction is this, I would clearly, I have lost a pi bond. I must have clearly incorporated HCl, so this is an addition reaction. It's not hard to tell, there's also a rearrangement. I've gone from having a 5-membered ring with a 3-carbon appendage to a 6-membered ring with a 2-carbon appendage. So this is an addition with rearrangement. Now, if I wanted to be anal, and the question was to, as completely as you can, describe this reaction, I would say that this is a dehydration rearrangement. For this one, I would call a hydrochlorination with rearrangement. So I'd specify the kind of addition reaction. So it's a hydrochlorination with rearrangement. So those are the 4 classes of organic reactions, right? There's substitutions, which I can subclassify, additions, eliminations, and rearrangements. And often rearrangements are accompanied by other kinds of reactions. Alright, so we've looked at the different types of reagents, nucleophiles and electrophiles. And we've also looked at the types of organic reactions. What we're going to look at now would be the types of organic intermediates, types of organic intermediates. And really more specifically, I'm going to look at, what we're looking at is the carbon-based intermediates. Right? Because there are several intermediates in organic chemistry where the intermediacy is because of the N or the sulfur or the O or whatever it is. So we're looking at the carbon-based intermediates. Alright, so organic chemists then, just to remind you, where's my cursor? The organic chemists then, just to remind you what are intermediates. So intermediates then are minima that arise between 2 maxima. So I'll have enthalpy on that axis, I'll have reaction coordinate on this axis, and if I have a synchronous reaction, it has no intermediates. On the other hand, if I have a reaction in which there is a minimum between the maxima, and this is not very smooth, then if I have a minimum here, then I have reagent, transition state 1, this is intermediate, transition state 2, this is my product. This will be reagent, transition state the only one, and my product. So this is the intermediate. It's a minimum that exists between 2 adjacent maxima. Well, the carbon-based intermediates are of 3 types. They are R+, which are called carbocations. They are R-, which are called carbanions. And they are R-, which are called free radicals. These are the 3 most common carbon-based intermediates in organic chemistry. Now, There are others. In fact, there's one that we will see in second organic, and there are even others beyond those. But these are by far the most common carbon-based intermediates. So let's look at those three and give a bit more detail about their chemistry. So let's talk about carbocations. Well, the carbocation is a trigonal planar sp3 hybridized species that has an unoccupied, if you will, vacant p orbital, and it's got a positive charge. So the carbon of a carbocation, I'm going to draw it two different ways, right? The carbon of a carbocation only has a sextet of electrons, 2 in this bond, 2 in that bond, 2 in this bond. It's a sextet. And it's trigonal planar, it's sp2 hybridized, so it's sp2 hybridized, okay, and it's got a vacant p orbital. Now, carbon is not an electropositive element, so carbon then is not particularly stable with a positive charge. In fact, for that matter, carbon is not stable with charge at all. So carbocations then are hot species, in other words, they're unstable. So obviously something that's unstable can be stabilized by the medium. For example, sodium ions are stabilized by chlorides that surround them in the solid lattice, or they're stabilized, for example, by water molecules that surround them and solvate them in solution. So they can be stabilized by a medium or a matrix. Well, carbocations try to stabilize themselves also by a medium, but also by internal or intramolecular mechanisms. And the way they do that is either by resonance or by induction. So bear in mind, if I have a carbon that's sp3 hybridized, and I attach it, for example, to a carbon that's sp2 hybridized, this is sp3, and this carbon is sp2, well, what happens? Well, the sp2 hybridized carbon, having more s character, turns out to be more electronegative than the sp3 hybridized carbon. We talked about that at some length already. I'm going to rephrase that. I'm going to say the sp3 hybridized carbon, having less s character, or if you will, more p character, is more electropositive. In other words, alkyl groups, R groups, are electron releasing. They push electrons away from themselves. Now, what makes the carbocation unstable is its electron deficiency, or its electron paucity, which arises from two reasons. One, the fact that it's positively charged, which is a biggie, and two, because it only has a sextet of electrons, and what carbon wants most desperately is electron density. So what this means then is that the more alkyl groups that are attached to the carbon, the more they will feed the carbon and therefore stabilize it. So really then I can identify 4 different classes of carbocations which differ in their stability. The most stable of the lot would be those in which there are 3 R groups on the electron deficient carbon. Those carbocations are said to be tertiary carbocations. The second one would be those in which there are 2 R groups on the carbocationic site. Those are called secondary carbocations. And this is much the same way as I call alcohols tertiary and secondary alcohols, right? This is a tertiary alcohol. This is a secondary alcohol, right? Because that's my alpha carbon. It's got 2 R's on it, secondary. Alpha carbon, 3 R's on it, tertiary. This is in essence, I guess, my alpha carbon, and it's got 3 R's, tertiary, 2 R's, secondary, 1 R, and this would be a primary carbocation. And if it has no R's whatsoever, so it's just CH3, this is just the methyl carbocation. So carbocations then are of 4 types. The methyl, where's my cursor? The methyl, primary, secondary, and tertiary. And they become increasingly stable as we go from methyl to primary to secondary to tertiary. And reason 1 is that, well, the reason is that alkyl groups are electron releasing groups, We say alkyl groups are ERGs. They are electron releasing groups. So they dump electron density to the electron pore site, and by that process they stabilize it. What they also do is that in the process of dumping electron density in the carbon, what actually happens is that the charge on the carbon falls. So it's no longer a plus charge localized on the carbon. What you get instead is this. Because the R's have pushed electrons away from themselves, they acquire a delta plus charge. And because the carbon has gained electron density, its charge will drop from 1 plus to a delta plus plus. So in the end, rather than localizing the charge in one particular particle and therefore intensifying it and making it unstable, I have now smeared or dispersed the charge. And one of the most efficient mechanisms of charge stabilization is charge dispersal. So any mechanism by which we delocalize or smear or spread the charge will stabilize the species. We are stabilizing this positive charge by a process called induction. And induction involves the drift of electrons along a sigma bond. Induction is what's responsible for polarity in a bond. We mentioned that before. The reason the HCl bond is polar is because Cl has a greater electronegativity than H, so that Cl pulls electrons towards itself, creating a delta minus here and a delta plus charge. This is an inductive effect, right? And that creates an electron drift. That's exactly what's happening here. This carbon is more electronegative than that carbon. A because it's sp2 hybridized, and B because it's positively charged. And therefore, the electrons will be sucked towards the carbon or pushed by these carbons, resulting in a delocalization of charge and therefore a stabilization of the species. So for carbocations, the more R groups, the better. In fact, it turns out that normally the threshold for the existence of a carbocation is primary, so that methyl and primary carbocations do not exist. I'm going to put an asterisk by this one because there is an exception. Methyl and primary carbocations do not exist because they're too unstable. The amount of electron density that is provided by the single R, or God forbid no R's, is not sufficient, and therefore these do not exist. But secondary carbocations do exist, as do the tertiary species. So these are without existence, and there's one exception. And I can make secondary and or tertiary carbocations because they can be formed. So what does that mean? It means that if I were to look at a profile, if I'm going to form a primary carbocation, if I'm going to form, say, a tertiary carbocation, and let's say I'm starting off by some species here, this is the energy of a tertiary carbocation. Therefore, it is an accessible species. I can make it. This is the energy of a secondary carbocation. Well, that requires the input of a bit more energy, but I can access that one. A primary carbocation has that much energy, and to access it requires the input of way too much energy. Therefore, this is not a path that's observed. So primary, secondary, and tertiary. So I cannot make primary carbocations because it just requires way too much energy to make them. Okay, but I can in fact make secondary carbocations and tertiary carbocations. All right. So we mentioned that there was a caveat with primaries, and the answer, the caveat arises because of resonance. So for example, if I were to have this carbocation, this is technically primary, because here's my positive charge, and there's only one carbon bound to it. But because I have a positive charge, a single bond away from a multiple bond, there's going to be resonance. And resonance is an even more effective means of charge dispersal, because I can end up with a hybrid that looks like this. And I'm going to have half plus on this carbon and a half plus on that carbon. Now that's a much more effective delocalization of charge. The charge is now borne equally by these two carbons, and the electron density is spread between all three. So resonance is a much more potent means of charge stabilization. And resonance here involves drift of electrons, right? Involves electron drift along a pi system. So induction is electron drift along a sigma system. Resonance is electron drift along a pi system. Resonance is a much more potent stabilization mechanism than is induction. And the reason is because resonance involves the drift of electrons that are pi or that are lone pairs. So if I had OCH2 plus, this is also stabilized by resonance. And I can write R O double bond CH2 plus charge. So the real species, my hybrid, is RO CH2, and there will be a dot 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 between these, a delta plus here and a delta plus here. Okay? So resonance involves electron drift on a pi system and can either involve the movement of pi electrons or lone pairs of electrons. So in fact, we can understand then why resonance is more potent than induction, because we just talked about this in class the other day. In fact, I think it was today. That if I were to look at the hierarchy of my lone pairs, pi pairs, and sigma pairs in terms of the nucleophilicity, we said that lone pairs are more nucleophilic than pi pairs, and that sigma pairs were non-nucleophilic. And why was that? Nucleophilicity involves the system's ability to move electrons, to donate an electron pair. And the ones that are more easily donatable are the ones that are A, most energetic, or B, that are held least tightly. Lone pairs are bound to the molecule by the attractive pull of a single nucleus. So if you look at, say, this molecule, right, I've got lone pairs, I've got pi pairs, I've got sigma pairs. And if some electrophile would attack the species, it is the lone pair of electrons that invariably attack them to give rise to this as my entity, right? That's invariably what happens. So why is it that despite the fact that I've got lone pairs, pi pairs, and sigma pairs, why do the lone pairs attack first? And the answer is because they are the best at it. Because lone pairs are bound to the molecule by the attractive pull of one nucleus. So they're not held quite as tightly. Pi pairs are bound to the molecule by the attractive pull of two nuclei, but weakly so because it's a pi bond, for God's sake. Sigma pairs, on the other hand, are bound very tightly to the molecule by the attractive pull of two nuclei. So sigma pairs are non-nucleophilic. Well, that's exactly the same phenomenon that's happening in resonance. So if I have a positive charge, CH2+, and I have to try to stabilize it by induction. And what is induction? Drift of electrons along a sigma bond. Well, those are sigma electrons. Those are held tightly. Those do not respond as well to potential differences in the molecule. So yes, they'll move, but they won't move a lot. So induction will help, it just is not the best mechanism for charge stabilization. What about resonance? Well, absolutely, resonance would help because that involves moving pi electrons. Pi electrons are more energetic, they're also held more loosely, they move better in response to a potential difference. But even better than pi electrons will be lone pairs of electrons, because they are even more energetic than lone pairs, than pi pairs, and they are held least tightly, so they can respond better to electron deficiency or potential differences in the molecule. So it's exactly the same trend. If I understand what is at work here in the ordering of lone pairs to pi pairs to sigma pairs, I could have said that in terms of nucleophilicity, these are the most nucleophilic, these are the least. In terms of stabilization of an adjacent positive charge, these are the most effective, those are the least. If I were to talk about basicity, and bases are also electron pair donors, that's the most basic, these are the least basic. So I don't have to learn the trend for three different phenomena. If I understand the trend and what is at work, I can make an intelligent assessment of how each lone of each type of electrons, how effective they are with respect to that phenomenon, whether it's resonance or versus induction or nucleophilicity or basicity or so on. There's one other point we need to make about induction and resonance, and that is induction is an effect which has a limited geography. So it's very strong along the first bond, modest along the second bond, weak along the third bond and basically disappears. So if I have, for example, a delta minus 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 on the chlorine, it will induce a delta plus 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 on this carbon, a delta plus plus on this one, a delta plus on that, and then these don't feel the chlorine at all. In other words, the chlorine here pulls a lot from this carbon. This carbon in response pulls some from this carbon. This carbon, having lost electron density, then pulls a little bit from this carbon, and then the effect is lost. So induction is strong along bond 1, modest along bond 2, weak along bond 3. Resonance, on the other hand, has no such limitation. And as long as I have conjugation, in other words, as long as I have a plus charge, a single bond with a multiple bond, I can have resonance. And that can go on ad infinitum. So what does that mean? Well, I can draw this resonance form, and I won't really draw all of those things again, right? Oh my God. So what this means is I have a plus charge here, and then double, 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 all the way across. Then I can move this one here and get a plus charge here, this one here, get a plus charge here, and so on. So what I end up with then is a hybrid. I'll get a hybrid that looks like this. Dot 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 all the way across, with a positive charge delocalized over this system. So I'll have delta plus here, 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 and so on. That effect can continue across 1,000 carbons, across 1 billion carbons, across 1 trillion carbons. It does not matter. As long as I have the conjugate, which is alternating double, single, and double, single, double, single. In other words, as long as I have conjugation, right, which is alternating, that's alternating double and single bonds. So the two differences between induction and resonance are, induction is weaker than resonance because it involves only the drift of sigma electrons, which are held very tightly, and therefore are less responsive to potential differences in the molecule, whereas resonance involves the drift of pi electrons, or drift on a pi system more correctly, and that is much more potent, and also resonance is unlimited in terms of distance. The range of resonance is much, much greater than the range of induction, which is typically a 3-bond, maybe 4-bond phenomenon at best. Resonance is an N-bond phenomenon, where N really just goes on and on and on and on. Alright, so one sort of intermediate we've looked at then is the carbocation. We've looked at the mechanisms of carbocation stabilization, and we saw that for carbocations, tertiaries are more stable and secondaries more stable and primaries and so on. And the question is, well, where then do carbocations like this one, this is called the allyl cation, where do they feature in the hierarchy? Well, it's not surprising that carbocations like allyl, and another common one is benzyl, which is a positive charge that's adjacent to the benzene ring. Right, this is called a benzyl cation. That these are going to be very stable. And in fact, a good argument is that these are a little bit more stable. They're a little bit more stable than tertiary carbocations. So allyl and benzyl are a little bit more stable than tertiary carbocations. So even though they are primary, they are resonance stabilized. And resonance stabilization is so potent that it beats primary inductive, it beats secondary inductive, and it actually beats tertiary inductive as well. So they're greater than or about as stable as tertiary carbocations. Okay, so those are carbocations. The other class of organic intermediates are carbanions. And unlike carbocations, which were sp2 hybridized in trigonal plane with a positive charge, these are generally R3C minus. The carbons are sp3 hybridized, And these have the following shape. They've got a carbon, which has a lone pair of electrons, and then it's got some number of R groups on it. So, and it's got a negative charge. This carbon has an octet, it's got 2, 4, 6, 8 electrons. We can rank these then as CH3 minus, the methyl carbon ion. I can have RCH2 minus, this would be called a primary carbon ion. R2CH minus, this is a secondary carbon ion. And again, R3C minus, this is a tertiary carbon ion. Well, how would I rank carbon ions then? Well, in terms of energies, what I find, how did I do the first one? Stability? I don't recall. Stability. So in terms of stability, I find that the order in fact is inverted. So CH3 minus is more stable than primary, than secondary, and tertiary. Well, why is that? Well, here the carbon is negatively charged. Carbon does not like being charged, positive or negative. But at least in this case, the H's are not amplifying the negative charge in the carbon. Now, they're not helping, but they're not hurting. On the other hand, in a primary carbon ion, the R group, as we said, is electron releasing. So what it's doing is, it is dumping even more electron density onto a carbon that's already negative, therefore amplifying the electron density of the carbon. That's intensifying it. That's bad, because really what I want to do is to stabilize it. How do I stabilize it? By spreading it. This is doing exactly the opposite. I'm concentrating the electron density on the carbon. And the more R groups I add, the more I concentrate it, therefore the more I destabilize it. So the least stable carbon ion is a tertiary carbon ion. Now, by the way, and I guess it didn't need to be said, but carbon ions would be considered nucleophiles. Right? These would be very potent nucleophiles because they are electron rich. The carbon has a lone pair of electrons, and the carbon desperately wants to get rid of it because it's not an electronegative element. On the other hand, carbocations, and I didn't make that point earlier, but I'll make it now. Carbocations are curious. Carbocations are electrophiles. Right? Carbocations will be electrophiles because the carbon is A, positively charged, and B only has a sextet of electrons. So they, by definition, electrophiles. And they're very potent electrophiles. Now, what does resonance play a role here? Well, if I had a carbon ion, that can also be stabilized by resonance. My arrows go this way. And therefore, resonance is a very potent mechanism for stabilization of carbon ions, whether it's by allyl or by benzyl. So in terms of the energies, how do I have stability? In terms of stability, the resonance stabilized carbon ions are actually the most stable. Then there'll be methyl, then primary, then secondary, then tertiary. Alright, so the last class of carbon-based intermediates are the free radicals. Jeez, my screen is twisted. The last class of carbon-based intermediates, I did it again, are the free radicals. And free radicals are, I'm going to write R3C with a dot. So these carbons are by and large sp3 hybridized, although there's some good evidence that it's actually not, but leave it as sp3 hybridized. The carbon has a septet of electrons. So I have a carbon that has 3 groups on them with a dot. So again, this could either be H's or R's. So the categories of my free radicals then go much the same way. I can have a tertiary free radical, which I'm just going to write as R3. Well, for this one I'll write 3. So it's R3C dot. This is tertiary. I can have secondary. I can have primary,
and I can have methyl. The question is, what are their relative stabilities? As it turns out, their stability mirrors that of the carbocations, and it's not surprising why. Even though free radicals do not have a positive charge, as do carbocations with their cousins, secondary, this is primary, this is methyl, free radicals are electron poor. The carbons only have a septet of electrons. The carbocations, the carbons only have a sextet. But the point is they're both electron poor, which means anything that dumps electron density towards the electron poor side will stabilize the system. And the more R groups I have, where's my cursor? The more R groups I have, right, the more they dump electron density towards the electron poor side and therefore stabilize it. So the most stable free radicals are tertiary, much like carbocations, followed by secondary, followed by primary, and then the methyl radical is the least stable. One big difference between carbocations and free radicals is that R3C plus is the most stable, R2CH plus, then RCH2 plus, and CH3 plus. Whereas, unless they were resonance stabilized, primary and methyl carbocations don't form. All four of these have a real world existence. So why is it that their cousins, the order of stability is exactly the same, but the existences differ? I can only see tertiary and secondary carbocations. I cannot see methyl or primary, unless the primary is resonance stabilized. But I see methyl radicals, primary radicals, secondary radicals, and tertiary radicals. Why is it that all four of these have a finite existence? And the answer is very simple. The instability of a carbocation is twofold. One, they are positive, and two, they're missing two electrons, right? Carbons will have a sextet. So these are hotter species than the free radicals. On the other hand, the free radicals only are missing one electron, and they're not charged at all. So yeah, they're not stable, but they're not horribly unstable. These are horribly unstable. So while I cannot see methyl or primary carbocations, I can see methyl and primary free radicals because they're not quite as hot a species as the carbocation. As always, resonance is an excellent means of stabilizing free radicals, as they do for carbocations and carbanions. This time I'm going to use the fishhook because I'm moving a single electron. And so the hybrid will look something like this. Most people just sort of write a delta dot. But that still involves delocalization of the lone electron and therefore increasing stability. So tertiary free radicals are about as stable as allyl radicals. Right? The stability is about the same way. So the three carbon-based intermediates then are free radicals, carbocations, and carbanions. We understand the conditions under which we generate those intermediates. The conditions under which the intermediates, how they're stabilized. And the very last thing that we'll talk about is, which time do we have? The very last thing we'll talk about is bond breakage in organic chemistry. So, bonds in organic chemistry can cleave or break or lyse in two ways. So if I have, for example, a homonuclear bond, that bond would break in such a fashion that A takes one electron and the other A takes the other electron. So what I'll get from this is two A dots. So normally in the AA bond, there are two electrons. Since each atom of A has the same electronegativity as the other, when the bond breaks, each A gets one. And that leads to the formation of two like species, both are free radicals. This is called homolysis, or homolysis, if you will, or homolytic cleavage. lytic cleavage. So for example, if I take the interhalogen BrCl and I expose that to light or to heat, what I'll end up with is the cleavage of the BrCl bond to give Br dot and Cl dot. So notice in that case, the bond is not entirely non-polar. There is a slight dipole on the BrCl bond, but it's only a slight dipole. And secondly, you notice I did not draw both fish hooks this time, because it's understood if one electron goes here, the other one must be going on the bromine. And this is also homolysis, even though I didn't make two Brs or two Cls. The point is, the species generated are both free radicals. So cleavage that generates the same kind of species, same kind, is called homolysis or homolysis or homolytic cleavage. Well, under what conditions would I get homolysis? And the answer is 1. The bond under consideration must be nonpolar. So the bond must be nonpolar. The conditions require heat or light. And 3, the reaction happens in nonpolar solvents or in the gas phase. Well, it's easy to see why the bond must be nonpolar, because obviously I want to have each atom pulling, if not exactly the same, then darn near close to the same. That way each will get one electron. That will only happen when the system is nonpolar. So I would not get homolysis, for example, where's my cursor? I would not get homolysis of an HCl bond where the electrons are already this close to chlorine, because that will require the H pulling back one of those electrons, and that's not going to happen. Heat or light are typical conditions for homolysis, because I tend not to use other reagents that would bring about bond breakage, and I'll show you what that means in a second. And then I also would use non-polar solvents or reactions in the gas phase. And why is that? Well, certainly gas phase means there's no intermolecular interaction, because one molecule does not feel the other in the gas phase. There's no interaction in the gas phase. But the solvent is important too, because let's imagine I have let's say a BrCl bond. But I put this, let's say there's a very slight delta minus on the bromine, on the chlorine, and there's a slight delta plus on the bromine. Well, if I have this in a system, in a solvent which is itself polar, let's say I have a delta minus and a delta plus of my solvent. The delta minus of the solvent will orient itself towards the delta plus of the Br, and similarly, the delta plus of the solvent will orient itself towards the delta minus of the chlorine. So what will happen? The delta minus will attract the delta plus, the delta minus will attract the delta plus, which means the delta plus starts sucking the electrons this way, and that in turn starts sucking them that way. The delta minus, right, will then repel the electrons. They will in turn move the electrons that way, and the net effect is I will enhance the polarity of this bond. So if I want to encourage homolysis, I want the bond to be as non-polar as possible. If I put it in a polar medium, the polar solvent will induce a greater dipole on the bond. So polar solvents tend to enhance the dipole of bonds. So we'll take a bond that is essentially non-polar and try to induce a dipole on it. Or we'll take a bond that is slightly polar and induce a greater dipole on it. That is counter to what I need for the bond to undergo homolysis. So in order to encourage homolysis, I want my bonds to be non-polar. I want my solvent to be non-polar, or better yet, no solvent at all. So there's no other molecule in the system that can mess with the one I'm looking at and cause any perturbations in the bond or in the bond. Similarly, I'll want my reagents. Well, I will tend to use high temperature and heat. In other words, I use a large amount of energy to cause fission of the bond. The other kind of bond breakage is called hetero.
Auto shutdown sequence in progress.
So I'll just spend another 2 minutes. It's called heterolysis, or heterolysis, or heterolytic cleavage. Heterolytic cleavage. This involves, for example, the say HCl cleaving to give rise to H plus and Cl minus. Now this generates two different kinds of species. I make a cation and I make an anion. So those are two fundamentally different species. That's why it's called heterolysis, because it's cleavage leading to two different kinds of species, a cation and an anion. Whereas in homolysis, it was cleavage leading to two like species that were both free radicals. All right, they were both free radicals here. Well, under what conditions would I get heterolysis? And the answer is, one, I must use polar bonds. Whoa, that's exciting. It would be polar bonds. I would use polar solvents, obviously, because I want to enhance the polarity of the bond, and I use ambient conditions. So I don't use light, and the temperature I use tend to be, usually 100 degrees Celsius or less. And those are the conditions that encourage heterolysis. It stands to reason, just very quickly then, it stands to reason that to get a carbocation, I would take, for example, Rx, and I would break the bond to give R plus and X minus. That's one way you can get a carbocation. To get a carbanion, for example, I might do something like this. I might have some base come in, pull off the proton, dump the electrons onto the carbon, and I'd get R minus. But to get a free radical, I would typically have, for example, let's say Cl dot come in and do this, and I get R dot. And in this case HCl, in this case I'd get BH. Okay, so carbocations and carbanions form by two electron motion. Right? Two electrons either moving away from R to give carbocation, two electrons moving towards R to give the carbanion. Free radical formation involves single electron migration, a single electron moving towards the R to give rise to the free radical. So this is a homolytic process. These two are heterolytic. So these are heterolyses. This is a homolysis. So we'll stop there. I'll see you guys next day.